right, Professor Hildebrandt here. Lecture videos on Chapter 9, and probably the first of a series of videos to get us through the rest of the semester during this time of transition. I just tried to record this presentation, spent a lot of time on it, and realized it didn't record. So hopefully my second take is better. But in this first video for Chapter 9, I'm going to focus on the first two learning objectives. Really quickly, we'll establish what a point estimate is, and then we're going to talk about confidence intervals for population means, and we'll have two different methods for calculating those. So if you think back to the last chapter in Chapter 8, we assumed that we had a lot of information about our population, that we would know its mean, its standard deviation, and these would tell us things about the population shape. And so we could use that information. But the reality is that that's just not often the case. It's not often true. And so instead, we use what's called a point estimate to estimate our population. And this is something we've talked about before, right? The idea of sampling. And so like we have, Barbados wants to know how much money tourists are spending. Well, they can't reasonably talk to every tourist that leaves their country, but they could randomly select 500 people as they depart and calculate an average amount of money spent on the island from that sample. And so that's all we're going to do. That's all a point estimate is. The point estimate is just the statistic that we're using to estimate our population's parameter. And so we're going to use some statistics from our samples to try to estimate our population's mean. So our next learning objective here is then confidence intervals. So it's going to be this range of values, and we expect that our population's parameter, in this case the mean, will fall within this range. So we'll have a minimum, we'll have a maximum, and we think the population mean will be somewhere in between. We're going to have two different situations for calculating these confidence intervals for the population mean. In the first method, we're going to at least know the population standard deviation, and so we'll be able to use that hopefully now familiar Z distribution table. But then we're going to have a second method where the population standard deviation is unknown, and so we're going to have to use a new tool to help us in those situations. There are some factors that determine the width of the confidence interval, such as the number of observations in the sample. So we saw also from Chapter 8 that the larger our sample was, the more representative it was of the population itself, right? And so when we calculated things like the sample mean, if the sample was larger, then the sample mean was more likely to be highly representative of the population mean. Smaller samples were not as effective, okay? And so we also will talk about different levels of confidence. We can go as high as a 99% confidence level. We can go down to an 85% confidence level. And then so there'll be differences there. So here's our first method, trying to calculate these confidence intervals when we know the population standard deviation. And so for these, we're just going to use that familiar Z distribution. And here's the formula that you're going to need. Recalling that X bar is your sample mean. And because we're doing a range, we'll do plus and minus that Z value times the population standard deviation. So see, we have to know that in order to calculate using this formula. And then we'll divide that by the square root of n, where n is the number of observations in our sample. And usually we're going to know the population standard deviation if this is if whatever we're studying is something that has a long history of collected data that we can pull from. And so that's going to allow us to use the standard normal distribution. That's going to allow us to use that Z chart. So here's how we're going to go about finding the Z value for different confidence levels. So let's start with, we're trying to find the Z value for a 95% confidence level. So first we just need to convert this percentage to a non-percent value that would be representative of the area under the curve. So we'll take that 95%, divide by 100 to get 0.95. And again, recall that because our mean divides the area under the curve in half, so we have 0.5 values on the right side and 0.5 under the left side of the curve. Then we're going to take this 0.95 and divide by 2. And so the area that we're trying to represent is 0.4750. So remember, and we've done this a little bit, but this is working backwards, right? Usually we started with a z-score, and then we were trying to find the area under the curve. Here we have the area under the curve. That's that 4.750, and we're trying to use that then to determine the z value. So going to our z chart, here's a snapshot of it, right? Now's probably a good time, if you don't already have it, to pull out a z distribution that you can reference during this video. So here's that area though, 0.475. So we go over and we see a value of 1.9. We go up and we see 0.06. And so our z-score here is 1.96. And this will always be the case. If we are calculating a confidence interval at the 95% level, when we know the population standard deviation, the z-value that we use will always be 1.96. But if you can't remember that, that's okay. You just use these steps to find it. So let me show you another example here. What if we wanted to do the same, but we want our confidence level, it doesn't have to be as high. We only need an 85% confidence level. So again, first we're going to calculate or convert that value. So we take 85 and divide by 100 to get 0.85. And then we're going to, again, divide in half to get the area under one side of the curve. And so we're looking for the z value that corresponds to an area under the curve of 0.425. And so if you look at your z chart, you would find that z value to be 1.44. Pause this video right now, please. Go look at your z table and make sure you can do this, because you're going to need to be able to find these values in order to work your problems for this chapter. Okay, so let's pull all this together with an example. So we have the Management Association. They're studying the income of retail managers. They do a random sampling of 49 managers, and they get a sample mean income of 45,420 with a standard deviation for the population of $2,050. Okay, so first question, what does the population mean? Well, the answer is we do not know, but we can use the sample mean, that 45,420, as our best estimate. Okay, question 2. What is a reasonable range of values for the population mean? So here's where we calculate the confidence interval. So using our formula from the previous slide, we take the sample mean, 45,420. We do plus or minus. We already found the z that corresponds to a 95%, right? Confidence level is the 1.96. Multiply that times the population standard deviation of 2,050 divided by the square root of the sample size, which is 49. And so we get 45,420 plus or minus 574, and we call this 574 the margin of error. And so our confidence interval then is 44,846 up to 45,994. So looking at a second example, work out another one. The management one was worked out in your textbook. I'm going to work out a second one, hoping if we go through it a couple of times, it'll help. So we're going to take a sample of 81 observations taken from a normal population with a standard deviation of 5. We find our sample mean to be 40. All right, we're again looking for a 95% confidence interval for this population mean. So the first step, if we didn't already know it, would be to calculate the z value. Well, it's the 1.96. And then once again, we're going to use this formula. So we plug in the sample mean of 40 plus the z value of 1.96 times the population standard deviation of 5 divided by the square root of the sample size 81 up here, right? Which is 9. I just didn't want to type out that formula. So we would get a min of 38.911 and a max of 41.089. Okay, so now let's look at the second method, trying to calculate a confidence interval when we don't know the population standard deviation. And honestly, in most sampling situations, this is probably going to be where we are. We're not going to know the population standard deviation. And so we can't use the formula that I just showed you. Instead, we're going to use not only the sample mean to help estimate the population, but we're also going to use the sample standard deviation to help estimate what's going on with this population. And so we will now use something called the T distribution. So it's going to be a new chart. It's in one of your appendixes in the book. You can also Google it. You probably want to have one of those saved on your computer or print one off as you're working through these problems. And so here's the formula that we're going to use. Similar to the last one, right? Really all we've done, we replaced our Z with a T. And then up here where we used to have our population standard deviation, now we have this lowercase s, which remember stands for the standard deviation of the sample. A few things about the T distribution. It's actually very similar to the ones we've been working with, the standard normal. It's got a continuous distribution. It's mound-shaped. It's symmetrical. There's a family of them, just like there was for the standard normal distributions. But the difference is it's flatter or more spread out because it has a larger standard deviation than that of the population. And so you can see as we look at them here, the Z distribution, this green line, and then the T distribution, it is flatter. So how do we go about finding the value of T? Again, if you haven't already, please get yourself a T distribution chart that you can reference. We are going to be assuming in these problems that our population is normal. And yeah, there's your appendix specifically. It's Appendix B5. This one is set up a little bit differently, okay, than the Z distribution. So the first thing you're going to do is look across this top row, and this is the percents for the confidence intervals. And so whichever one you're wanting to use, if it's 95, well, then you're going to go down this column here. That's somewhere where your T value is going to be. Okay, so that's step one, is find the column that represents your confidence level. Then you're going to find what we call the degrees of freedom, which is simply taking your sample size and subtracting 1. So that's a very easy formula, right? N minus 1. So suppose our sample size is 10. Well, then our degrees of freedom, right, would be 9. So here's my 9. And if I go over, I would find that the area under the curve would be, the T value would be 2.262. So that's the T value that we would use for a 95% confidence when our sample size is 10. So let's try finding a couple more of these T values. Suppose we have a sample size of 6 and a confidence interval of 90. Well, here's my column for confidence interval of 90. If my sample size is 6, then my degrees of freedom are 5. And so I would find it to be 2.015 would be my T value. What about a confidence of 99 and a sample of 7? Well, here's this last column here is my confidence interval of 99%. A sample size of 7 would mean we're going to go with degrees of freedom would be 6. And so our T value would be 3.707. And so just remember to find the degrees of freedom, it's N minus 1, where N is equal to your sample size. All right, so let's work out an example. This is the one from the textbook. So they're talking about the tire manufacturer wants to know the tread life of its tires. It takes a sample of 10. So there's our sample size, sample of 10, driven 50,000 miles, and they revealed a sample mean of 0.32 of an inch with a standard deviation of 0.09. And they're asking us to construct a 95% confidence interval for this population. So here's again the formula we're going to use. So we plug in that sample mean of 0.32. We already found earlier, recall, when I first showed you how to find a T value, we did a 95% confidence interval with a sample size of 10, and that corresponding T value was 2.262. And then we multiply times the sample standard deviation of 0.09 inch divided by the square root of 10, 10 being, again, our sample size. And so here we would have 0.32 plus or minus 0.064. And so this 0.064, again, is what we call the margin of error, okay? And so what's our range? Well, our min then is 0.256 and our max is 0.384. But then we're asked another question. It said, would it be reasonable for the manufacturer to conclude that after 50,000 miles, the mean amount of tread remaining is 0.3? Well, does 0.3 of an inch fall in this range? Yes, it does. And so it is possible that the mean of the population after 50,000 miles is 0.30 of an inch. Okay, so one more example here that we're going to work. So suppose we have a sample of 16 people, and we find that the sample mean is 45 gallons of milk consumed with a sample standard deviation of 20 gallons. We're assuming again that the population distribution is normal. Let's answer a few questions. So what is the value of the population mean? Well, again, it's unknown, but our best estimate here is 45 because that's our sample mean. Okay, well, if we're doing a 90% confidence interval, what's the value of t? So you're going to pull out your t distribution chart. You're going to go to the column that represents 90%. And then for your degrees of freedom, remember it's n minus 1. So you're going to be using 15 for your degrees of freedom. Well, you will find a corresponding t value of 1.753. All right. So then let's develop a 90% confidence interval for this population. So again, we're going to use this formula here. So we plug in 45 for the sample mean, plus or minus. So this should be a minus. Sorry, error there, guys. Our t value we found to be 1.753. Multiplying that times 20, the sample mean, divided by the square root of our sample size, which was 16, the square root of 16 being 4. And so we get a minimum of 36.235 gallons and a maximum of 53.765 gallons. And so our final question here, would it be reasonable to conclude that the population mean is 48 gallons? And the answer is yes, it absolutely would be reasonable because 48 gallons falls within the confidence interval, and we're about 90% confident that would be the case. So that wraps up the first half of Chapter 9. Be looking for Part B coming up to finish out this chapter. If you have any questions, please send me an email.